Hello everyone, and welcome to my video presentation for content-based image retrieval, CBIR, using color histograms. This is a presentation midterm project for CMSC 630 image analysis, and my name is Michael. This is my presentation. So some background. How can we search for images using an example image instead of keywords? The solution, content-based image retrieval, CBIR, is a system that finds images based on their visual content, color, texture, shape, rather than keywords. It's important because it features things like reverse image search, and it helps organize large media libraries, and it's used in the fields of e-commerce, medical imaging. But it also it's important because it bridges the gap between human language and visual context for being able to search, and it's a really important tool in that regard. Project goal is to build a functional CBIR system in MATLAB that retrieves visually similar images from the database using color histogram features. And some literature review. So let's talk about some historical foundational approaches for CBIR. The method color histograms, pioneered by Swain and Ballard in 1991. CBIR was really big in 1990s. It's really powered today by deep learning a lot, but they pioneered this method in 1991. The strength is it's simple, fast, robust to image rotation and scaling. The weaknesses are it ignores spatial layout where the colors are, but I didn't really see a lot of that in the testing for this. In the small data set that we used, there was only about 100 images, and I was able to get pretty good recall from the model that we had in MATLAB, but this can be a critical weakness when we're talking about scaling in mass. Texture features, you can search by texture rather than color. Talking about like rough or smooth. The method is there's Gabor filters or local binary patterns, LBP. The serious drawback though is it can be more expensive computationally. So depending on the project where you are trying to search for textures, this can cost a lot more computationally. So scalability wise, it can be a little dubious. Excuse me. Because it is so computationally expensive. So that can be a major drawback. We can also search by shape features. Methods like edge detection, and Fourier descriptors. The strength is it's really effective at object recognition. The weaknesses are, though, it often requires image segmentation first. So to have a lot of success with this, you may need to do a bit of pre-processing, which can be a little bit of a trade-off depending on the application. Excuse me. In practice today, Google, the search by image feature. This is really popular, so you can just drag a picture into the search bar rather than actually using words, and this can get you an exact replica, and you can see where an image is across the internet, and that's an incredibly practical application. And also Pinterest, where you can search by visual interests rather than just keywords, and this allows users on this platform to really, have more than one powerful search mechanism. And again, this today is these methods are really boosted by deep learning algorithms to really bolster the effectiveness. So for this project, the system architecture, it was 6 steps, but I really put it into 2 phases: an offline phase and an online phase. For the online phase, it was about building database to compare the query images to. so that when we're running the query live, it's much faster doing that pre-processing of the data. So pretty much the goal of the offline phase, like I was saying, was to process every image in the data set and store all their features in the 100 by 64 matrix. The 6-bit image has the 64 color combinations and 100 images. So that's the resulting matrix of the processing. Each row is the feature vector for those images. And again, like I said, that speeds things up incredibly so. And so online phase was actually taking the user's query image and making the active comparison based on Euclidean distance to every image in that database. Computes the distance to all 100 database vectors, ranks the results, and it also displays the top 20 visually as well. So we'll get a little bit more into the core components and the code of this implementation. The feature extraction, which is really important. This is the getting the histogram counts from the 6-bit images, for which we had our RGB2C, or the function there that converts our RGB images to 6-bit. And then this gets the histogram count from that 6-bit image. And so this is one of the key components of the project, was getting the features from the image. It takes an image and returns a normalized 1 by 64 feature vector. And like I said in the previous slide, you have 100 of those. It's 100 by 64. Key implementation detail. Normalization is crucial. We ensure size invariance by dividing the raw pixel counts by the number of pixels. So this is super important. Size invariance is basically being able to tell if an image or a similar image is the same, if they're at different distances. If your hand is super close, it may look bigger, and if it's further away, it may look smaller. But size invariance, we need to make sure that we can tell that if an image is distorted or if it looks further away, that this model can handle that. And the key part of this was to make normalization. This ensures that this will, and there's actually a really good example of how normalization plays a process. In my second query, on my final slide, I'll show you the example of how it showed the invariance of one of the results. So yeah, we just had the total pixels. We divided everything by the total pixels, and this helps with normalization, which is, I can't stress enough how important. Similarity measurements, CBIR.M, we calculate similarity, finding the Euclidean distance between the query vector and every row in the column. That's how we're making the comparison, is by the Euclidean distance. And so the other key part of my code is this loop, which compares the query image against every image in the database using that Euclidean distance. So results and analysis, precision and recall is what I used for this measurement. So the precision formula is the relevant retrieved over total retrieved, and the recall is the relevant retrieved over the total relevant in the data set. For my testing, I had perfect recall. So there were duplicate images in the data set. They were like spam pop-up ad messages if you look through them. And there's multiples. For the first one, the query image, the 101.jpg, there's actually 10 total. So 9 results because the query image isn't counted in that. So you got 9 out of 9 recall. So I did make an assumption here, which we are allowed to do, that anything that wasn't a perfect match, considering there was duplicates, is not considered a precision hit. So even though that we got some similar results in like this case one, like it gave other green ads, the not duplicates, I only counted for this at 20 results. I only counted the exact matches just for this formula. But obviously, if we're using different criteria, this is subject to change. You could say, how many relevant things with the features that you were looking for. So, I mean, it really depends. But for this, precision at 20, you'll see there was 9 images here. And then for my second, there was only 5 images in the database. So recall is 25%, 5 out of 20. Recall, it did catch all 5. But moving on. So these are the results. I'm going to go over that size and variance I showed you about. Let me zoom in here. And you can see this image right here, it's almost zoomed out. And he looks almost further away. And so the model was able to catch that, even though it looks slightly different. It's a little bit of a different size. But it was able to catch that in the image. And that's exactly what I was talking about earlier, that size and variance. I wanted to show that example. So also this is the first. This was the first query. You can see that, like I said, there was 10 in the database. They're all spam pop-up ads. And as it listed all 9 of the other ones. So that's why I had the recall, 9 out of 9. And like I said, as far as precision, you can see that it did bring up other kind of similar ads that are green. So for precision, if you were just trying to get all green ads, I think that you would have a much higher rate. But just for the strict sake of, for the formula, I did only have the 9 out of 20 just for that sake. Conclusion. So what do we learn? Color histograms are fast, high effective, capable of producing really good results. In this instance, I had some very good results with multiple different queries. It can achieve high precision, even for less distinct queries, demonstrating its general reliability. I found it was very reliable for this small data set of 100 images. I found that I was not having any problems with the color. With the color side of this image recognition for this data set, I wasn't having any problems. The main limitation remains a lack of contextual understanding, which could become a factor when these things get more diverse. So, hybrid features, combine color, spatial analysis, relevance. I have to speed this up to get to my demo. So, here's my references, and on we go to the live demo. Okay. So you can see that I have some of my functions here. This is the RGB2C6CC. This is converting this to that 6-bit image, which makes the 64-bit histogram 2 to the 664. Here's our function for get histogram counts. Here's our getting distance. Here's a sample for getting a distance. And this was also a script that I used to build the database using our get histogram count and our RGB266 function here. So we'll go ahead and actually run this script. We'll go ahead and run a couple of the queries. This is my fully functional cbir.m script. So we'll go ahead and run here. And we'll go to data. And we'll go ahead and do the query, the regular one. And we'll do 101. I have the first 20 come up in the command prompt for troubleshooting, which is pretty neat too. So yeah, here we go. Same thing as in the slide. We'll close that and we'll run another query really quick. Another quick query. Say that 5 times fast. Another quick query. All right, we'll go to 16. And we'll pick a random image this time. We'll do it with this guy here. Here we go. As you can see, it had one that was an exact match, and then the rest were a little similar, but yeah, that's that. I don't have time to do the exact accuracy on that second query that I did. But yes, I hope you enjoyed my presentation. I enjoy looking forward to hearing your questions in the discussion board. Thanks for listening, and have a great day.